Occasionally I receive email from Shippy about internship. Are you guys receiving similar email? Are you guys interested about internship? Do you guys receive email like this? You did? Okay, okay. So I guess it's I think email for everybody. I think it emailed to all the math major and also to CC to a couple of other you guys are on the mail list. So if you're in this class, maybe you are. That's what happens. I think many of her email offered opportunity internship. All right, for today's assignment, we are looking at a comparison test question. And here we are. Okay, if you look at it, it's a geometric theory, not geometric theory. It's an algebraic function that was in the theory. You have a polynomial in the numerator, and then in the denominator we have a root of polynomial. So the main concern will be the power. And then when n goes to infinity, the main concern will be the highest power. So as you're looking at the theory and try to find something to compare it to, question says use the limit comparison test. So if you want to apply the limit comparison test, the limit would be when n goes to infinity. So the main concern will be we want to compare this to something similar that is slightly easier to determine the convergency. We would choose the highest power. So we have n cubed in the numerator, and the denominator will be n to the 8th power square root. Square root of n to the 8th power would be what power? So numerator is power 3, denominator is power 4. you simplify that, you receive the power. So determine which one should we compare it to. It's basically analysis of the power, and that's something we often do when we study behavior functions. Correct? We have the highest degree, this is n cubed divided by square root of n to the eighth power. Square root of the half the power. So root of the eighth power is actually fourth power. So n to the power 3 divided by n to the power 4, that would be, it's n cubed of n cubed divided by n to the power 4. And you cancel the cube power, it's actually, right? N power 3 over n power 4. And n to the power 8 cancel. So it's 1 over n. That's what it should be compared to. And that's how we know it's actually divergent. And when you had it wrong, it's 1 over n. 1 over n.
Oh.
Okay. So the main idea is maybe so what we're gonna do is look at the function and try to think of when n goes to infinity, the leading term with the highest power leading term. So the numerator basically is n to the power 3. The denominator square root is square root of n to the power 8. So the root is half, so 8 half. That's n to the power 4 in the denominator. The numerator is n to the power 3. And this can be simplified as 1 over n. So what we are comparing this to, can't forget the summation notation. So it's comparable to the summation of 1 over n. This should be slightly smaller than 1 over n, but it's not smaller enough to make a difference. So this is divergent, and that's why this is also divergent, because they're compared. If you take the limit of this over the 1 over n, then we equal 1. So then we know these two are comparable. Summation, the answer should be A. The summation of 1 over n is divergent, therefore summation of this would also be divergent. So what I'm saying is that this is actually equal to infinity, therefore we would not have to calculate it since we knew it is infinity and summation. Okay, so that's really trying to figure out something to compare it to. We focus on the highest power because this has power function essentially in the numerator and in the denominator. After we analyze it, see which one it is compared to. Right. So far I have the attendance for today. Okay, any more question? Yes.
Last question.
You can say last question. I hope you're catching up because I realize in chapter 7, many of you are not completely done with chapter 7 homework. That's why it's still open. But let's try to catch up. Right. Your question with this one is, but you see, it's similar to the one we were just talking about. It's 3 over the denominator has. You look at the highest power in order to determine convergence divergence. So it's n times n times n, and the number is small enough for it to work. I mean, we're not calculating it. We're just trying to figure out something to compare it to. So we try to compare it. After comparison, we'll know whether it converge or diverge. If we knew it's convergent, then we might have to do the calculation. But if we knew it's divergent, then we don't have to do any calculation at all. So determining converge or diverge is the thing that we have to do first. So we figure out at infinity what happens when n is large enough. The one that matters, the one we should be compared to is 3 over. There's a root, and then you would identify the highest power. So this is legible. I mean, if you think about something, goes n times n times n. Okay, so this is really 3 over root of n. This is 3 over n to the power 3 half. The root will have the power. Okay, right?
No.
So what we're going to compare to, we are going to compare this with this. It's going to be a summation 3 over n to the power 3 half. It's going to be a p theory. The power is 3 half. The p is 3 half. N is from 1 to infinity. So the question is whether this is divergent. You know? Kylie, what do you think? P is bigger than 1, right? So we have that P theory. So according to our idea on P theory, if you get a summation of, it could be a number, it could be just 1 over n to the power P. Now P has to be bigger than 1. Then n goes from 1 or anything higher than 1 to infinity. This, we know for sure it would converge. That's what we call the P theory. If P is less than 1, it will diverge. But as long as P, which is the initial letter for the word power, is bigger than 1, it always converge. It has to be slightly bigger than 1. For example, it can be 1.01, it will still be converged. But if it's 1, that will be 1 over n, right? 1 over n summates added all together, that's actually divergent. But so let's say the borderline between converge and diverge, but equal to 1 is diverge, but anything higher than 1 in that power P, it will converge. So that one, 0 over 2 is bigger than 1, so it's converged, and therefore that converged as well. We can see that because this has a smaller denominator, so this actually have a smaller value than this. So if this is convergent, that so means this is finite. That is smaller than this finite number. Of course, it's also finite, right? Smaller than finite is finite, but bigger than finite may not guarantee finite. But anyway, that's really how we determine diverge. You find something that's comparable, and it's easy to determine converge and diverge. That way, so the comparable one, you're able to determine the ones. But for example, but the first thing is you got to be comparable. Whether they're comparable, you can do the linear comparison test to determine. So right now, we would say this is converge. See if we converge these or diverge. So we're not required to calculate it. And therefore, that's it. That will be question 12. Any other question?
It's here. Yeah, or problem 5.
Okay.
Like there's a part of it I don't understand what it's asking me to put in.
All right. Yeah. So use ratio test to determine whether this converge or diverge. For find the ratio of the successive term with the write your answer only simplified fraction. So the problem is if you are this an and an plus 1, they're both fractions. So when you divide one fraction over another fraction, that's what we call complex fraction. And that's why it says you have to write your answer as a fully simplified fraction. You know, when you do that, you have to simplify it. Yeah. So the first thing is to write the an plus 1 over an as simplified fraction. So here we're gonna do that first. So let's start that part. Just finish A first, and I'm going to think about the calculation. So the one that we are calculating is this. We don't have to worry about the negative sign, so we're going to just do the positive sign. So we have an plus 1, which equals, you can just write an first. An equal to. So we don't have any sign because we're taking absolute value here. So then the negative 5 to the power n, we're going to write it as 5 to the power n. because here we're just looking at F's value. So F's value of an would be 5 to the power n, and there's an n here, n times 5 to the power n, and then n factorial. That's how an looks like. We can, there's an n here, there's an n here. So the numerator and denominator both have n, we could cancel the n, right? So if we cancel the n, this is n, and then n minus 1, then n minus 2. The factorial is multiplication. So if we cancel the n, we have n minus 1 factorial. Everything else multiplied other than n. So n is canceled. Have 5 to the power n. That's an. And then we're gonna replace n by n plus 1. Now we're gonna write the value. There's the absolute value sign there because we're doing the ratio test. So we're gonna take the absolute value. And then we can have we're gonna follow this formula. We're gonna have n plus 1 replace n plus 1 minus 1 will be n factorial. The denominator numerator is going to be 5 to the n plus 1 power because the n is being replaced by n. So that's our one. And now let's do the division. So focus on the division because we're just trying to write the division there. So it's going to be an plus 1 divided by n. So you have 5 to the n plus 1 over n factorial divided by 5 to the power n over n minus 1 factorial. This is what we call a complex fraction because in the big division, there's a division and division equals. So there's a fraction inside the fraction, complex fraction. So we're going to try to simplify it. Number one thing is we can cancel the 5 to the power n. It's in the numerator and also in the denominator. So that's a common factor. You cancel the 5 power n. You have one factor of 5. You have 5 in the numerator. And then you can see the n factorial and n minus 1 factorial. They both have n minus 1 factorial, right? Factorial is multiplication, right? So simply there's a notation for multiplication reducing integer. So n factorial is n minus 1, n minus 2 until 1. N minus 1 factorial is n minus 1, n minus 2, 0. So this one is in this one. So n factorial has n minus 1 factorial. If we cancel n minus 1 factorial, the only thing left is n. So that will be how there will be n, there'll be 5, this will be n. And I think that's after it's simplified. That'll be okay?
Yeah, sure.
Okay, so once you have that simplified, then finding the limit is not that hard anymore because we're trying to find this limit when n goes to infinity. The limit really equals 0. And that's how we know it actually converge because according to the ratio test, the ratio is less than 1. Therefore, it's converging. Where less than 1 converge, bigger than 1 diverge, equal to 1. So, any question? So that answered this question. Any other homework question? So if there's no problem, we're going to continue where we left yesterday about the alternative theory. In this assignment, we are trying to differentiate them, but actually sometimes we're not able to avoid interaction or having something already talked about before it was introduced. Like the one we just mentioned here. This is actually an alternating theory, even though we don't call it that way. When we're studying the convergence of it, we actually took the absolute value and studied if the absolute value of the sequence is convergent or not. That's something that a little early since we have alternating theory section for assignment, but let's try. All right, so basically in chapter 8, the main focus is theory and kind of identify all the sections we're about to learn. We learned 8.1, which is introducing the idea of sequence. A sequence is a list of number that has some pattern in there. And so two of the common sequences, geometric sequence, arithmetic sequence. So hopefully we're able to if we knew what kind of sequence they are, we might be able to have an easy way to write their equation, write their formula there. 8.2 is the notion or the concept of a theory, which essentially is summation of infinite. In order to calculate the infinite sum, what we can do is to first figure out if there's any formula, any pattern in the partial sum. So S of n represents summation of the first n term in the theory, and then infinite sum, which is normally the notation is S. S is the actual infinite sum. And these two have the limit relation here. The limit of S of n is S. For any theory, there are two possibilities. It is either convergence or divergence. So you can use a adjective called convergent, divergent. So if the infinite sum is finite, and that's what we call it, converging theory. If it's equal to infinity, or if it has no limit value in the S of n, that's what we call divergence. So 8.1, 8.2 pretty much are conceptual understanding of the notion. And then 8.3, 4, and 5, we're starting talking about how do we know if a theory is converge or diverge. And so 8.3, we talk about two tests. One is the integral test. You turn the summation of the infinite sum into a calculation integral. If that integral is that there will be an improper integral since the upper limit is infinity. If that improper integral is finite, then the theory itself is finite, is converged. So if that integral is divergent, then the theory is divergent. There's a one-to-one correspondence in their convergency, but not in their value. The actual value are not equal, even if they are convergent. Another one is comparison test, which allows us to compare a complicated theory with a simplified comparable theory. That way we can determine their converge or diverge through their comparable theory. 8.4 is if you cannot find something to compare to, maybe you can compare with itself. So ratio test, you'll find the ratio between an plus 1 and an. If the limit of the ratio equal to a number that's less than 1, that guarantees convergence. The root test is similar. You take nth root of an if the limit equal to a number. If you have a finite limit that is less than 1, that we have a convergence theory. So those are some of the tests we talked about before. All right, and then 8.5, we're moving on to allowing the theory to have negative term. Before, we assume that we're talking about positive terms. But 8.5, we realize that we can turn alternating theory to a non-alternating theory and think about its behavior, and then adding the alternating facts to it. So that's where we were yesterday. Okay, so try to summarize what we've been talking about through the whole chapter 8. Essentially, we're trying to determine whether a theory altogether have the infinite summation or not. Okay, so we were trying to talk about some of the alternating theory allows us to study its behavior and also to have a approximation. So we define alternating theory as a theory that has positive term and negative term alternating in their sign. The format or the formula, either this way or this way, depending on whether the first term is positive or negative in the first term. And we had alternating theory test, which saying if you have alternating theory, as long as you can guarantee the positive part of the alternating theory is positive, decreasing, and living equal to 0, then the alternating theory itself converge. It will be convergent. So alternating theory test allows us to determine whether alternating theory is convergent or not. Okay. Then we practiced yesterday on how to apply the alternating theory test to determine convergency. And then here is where we start. The alternating theory approximation theorem is not on the determining whether it converge or not. We're saying suppose we will have an alternating theory that is convergent. So suppose we know the total summation is finite. Please. or this. We know it's equal to a finite limit, and that's assuming that finite value is L, right? So we're trying to look at what kind of error, or how much error we're making if you're using finite sum as an approximation of the infinite sum. So S of n is a finite sum. L is the infinite summation. So if you are using S of n to replace L, you're making a small error. Now, S of n minus L, that's how much error we're making. So we're saying that error is less than A sub n plus 1. So an plus 1 is actually the formula that's already in the alternating period formula. So we have that formula, therefore we have this formula. So now we have a formula to model the error that we're making in that estimation, in that approximation. Okay, so the first formula, equation 1, the first formula, the result number 1 is saying you use an plus 1 to measure the error. The second one is saying the L is right between S of n and S of n and n plus 1. We don't know which one is bigger, which one is smaller. It really depends on this case or that case. But the fact is how do we change the term? I believe if you start with a negative term, the total summation will be negative. And then we will get a little bit bigger, a little bit smaller, a little bigger, a little bit smaller, but overall it should be negative. Now, if you start with a positive term, and then you have positive, negative, but all the subsequent negative term will be smaller than the positive term. So because the first term is positive, the overall summation will be positive. So then, so depending on whether this two are small or big, and the L is right between these two. So these two will probably be positive or both negative, and L should be set, say between them. So the number 2 allows us to have a boundary for the L. It provided the left boundary and the right boundary for L. And then understandably, if n is really large, then S of n and S of n plus 1 are two numbers that is really close, right? So it's your accuracy is right right between these two numbers. This is super close. Of course, the L is really accurate. All right, and we were right here. Yesterday, we were talking about this one. We were talking about approximating this using how many term. So then the accuracy would be 2, the accuracy of 0.01. And we're talking about we got 9 terms. That will be accurate enough, right? And we can confirm that. Let's do it. Calculation. There's a couple of ways to do the calculation. Maybe we can use Excel. That way we don't have to we don't have to manually enter everything. Okay. You can use other data analysis tool, but right now that's the first thing I can think of. So we had this formula. Kind of think about first thing is we got know the n. And then we have n equal to, we have S of n, just call it Sn. And the formula is something is wrong with the way I do things. Right. The recording is really in the way. Make a copy of this into the Excel file, so we don't have to go back and forth. So I was just trying to do some calculation in here, but I don't want to do back and forth. So okay, that works. And then let's see. That's what we're gonna try to calculate. So we're gonna add a 9 term. So right here, I'm gonna try to type in what I want to calculate. So that was 1, 2. I guess I'm trying to add on to this is in spot A3. This plus 1. So 3. And I'm gonna do the same thing until A9. 9. Okay, so then we're gonna try to add the term. I guess when you want to add term, you have to add each term. S of n We also have to have it the an. An. Okay, so for example, when n equal to 1, it's negative 1 to the power 2, 1 over 1. So we would do, let's see, that was equal to negative 1 to the power of, with the power of n plus 1. N is in the spot A2 plus 1. Try to put in the an formula there. This is being multiplied by a fraction. The fraction is 1 over a n to the power 3. N is in the spot A2, and that raised to the power 3. That works. So equal to 1. And then we the reason I keep using A2 because A2 is where that particular n is at. Are we okay so far? So I'm entering that formula just so maybe that formula can be replaced, can be reapplied. Let's say if it works out, like see this one. In that spot, you can see the function negative 1 to A3 plus 1, A3 is 2, negative 1 to A3 plus 1, 1 over N3. So it's 1 over A3 to the power 3. So that looks like the right number. And you can see the alternating effect. So you can start with 1, negative, 1 A, positive, negative, positive, negative, positive. So it looks like everything works out. Yes. Okay. So now we can do a summation. So for example, this one is supposed to equal to, well, it can't equal, cannot put anything else. Or just equal to whatever in B2, right? This one equal to, I'm gonna try cumulative. So this number will add that number, right? We're adding these two. So then A2 is adding A3, which is really the A1 and plus A2. So that would be whatever in C2 plus that was in B3. So we figure out how do we calculate it, and then we can do the same calculation for the following spots. And this is adding each of these numbers, C5, B6, and C6, B7, with all that relation. So you can see it's converging. Are we okay there? Right, and then we can see the next number. It would be the same calculation. Again, going, and this keep going. Right, you can we're getting more and more accurate with this calculation. Yes, I should add more. Just so we can see the tendency of where it's going. This is right. We can see things are being more and more convergent, but you can see right at A9, the number is 0.902. The accuracy is up to 3 decimals. This one is up to 3 decimals. So after the A10, actually this is S of 10, it stabilized, right? The first 3 decimals is 0.901901. And you can imagine if we keep doing more calculation, the first 3 decimals are not going to change. What changes more accurate in the other table. So I think according to my calculation yesterday, the n will be 9. But look at the table, it looks like it's better for 10, right? At 10, it's where the decimal, in the 3 decimal, to be accurate, 0.0. It was stabilized. So I think the answer should be 10. All right, let's see. Let's review what we were doing yesterday. I mean, I was trying to go over the message here. So let's go back to this question. So we are trying to approximate the summation using the partial sum, and like how many numbers are we supposed to add so the total summation is accurate to 0.01. And I calculated, I feel like the 9 number added will be fine, but it looks like this will be better for 10. So I think maybe the rounding was the issue. Okay, so let's redo what we were talking about yesterday. It is So our intention is to use S of n to estimate the total summation. So suppose the total summation was L, right? According to alternating theory, approximation theorem, that result, S n minus L is less than a n sub 1. Right? So in order to figure out the right n, we would want this to be within 0.01. So this has to be less than 0.01, meaning our error can be smaller than 0.1, but we don't want it to be bigger. So I guess the problem that I did yesterday was making an equation. We should do an inequality instead of equation. So now here we're going to pay more attention on what is an plus 1. Now here is our an. So an plus 1 is 1 over n plus 1 cubed. So an plus 1 will follow an, and an, that's the an. So an is how we write an plus 1. It's supposed to be less than 0.001. And we do what we were doing yesterday, which is try to solve for n. This inequality, you can have multiple ways to solve it. Yesterday, I take cube root of both side equation, but in the spirit of keeping the inequality, let's multiply both side equation by the denominator. Then we have 1 is less than 0.001 times n plus 1 cubed. Right, and then we divide both sides by 0.01. You divide both sides by 0.1. 1 divided by 0. You get 1,000. We have 1,000 less than n plus 1 cubed. We can cube root both sides of the equation, then you have 10 is less than n plus 1. So then minus 1 on both sides of the equation, 9 is less than n. So as a consequence, obviously the n, the bigger the better, but maybe we should keep the n bigger than 9. So I did say within, so I feel like having an equation equal sign in that equality wouldn't matter that much. But this, I think it says within, I mean, maybe having equal there. So and the same idea as what we were talking about yesterday, I think 9 would be sufficient. Okay. We can also confirm with what the textbook is saying. This was one of the exercises in the book. Just wanted to be consistent, right? I actually already have the estimation. Too far. Alternating theory. This is the one we're working on. It is 9. Okay, you can see in the solution in the book also have a final answer that was S of 9. And you can calculate S of 9. It says it would accurate to 0.01 of the total sum. Okay. We also have that same solution. The S of 9 is 0.90112, which will be the answer to the question. I do feel like that would be more accurate than for, and that's S of 9. That was S of 10, right? The answer. It was 2116. So this one. 116, that was X of 9. This is the first question, and second question, I think will be slightly more complex because the log is in there. So in this question, the second question says we also wanted to be accurate to 0.01, and then you have this task of trying to measure the error. And we want to make sure the error is less than 0.01. So having that exercise run the same way, you can see the level of difficulty if the function are changed. This question, the 9 will be fine. That's the partial sum as approximation method. All right, so we repeat the same process for the second question. You will use the theorem saying Sn minus L, which is the limit value. You want it to be less than, well, it is less than an plus 1. And we want it to be less than 0.0. We want the error to be smaller than 1 out of 1,000. Now, this is the equation we have to solve in order to answer the question about n. So going back to the inequality, this is an, the positive part. So we know that an plus 1 will be natural log of n plus 1 over n plus 1. And that will be less than 0.001. Okay. So now we have an inequality that we need to solve. And in that inequality, there are two n. It is a little slightly harder to solve than the first one. Last example, in the first example, we only have one variable. In this question, we have two variables, there's two n here. So let's solve for the n. This is what people call transcendental equality because it's not algebraic. Can't not use polynomial to solve it. You might have to write equation to answer the question. But then we can also use number to answer the question. So I have this already open. So what kind of n will have natural log of n plus 1 over n plus 1 less than 0.0? We can try number, right? Normally we can try a large number. Let's see. I think we're gonna start with a 10, and let's see if n equal to 10, what will happen? Like n equal to 10, and then we have natural log of 11 over 11. We want to see how large this, whether it's less than 0.01 or not. Do a calculation or use this as our calculator. So right here we have our n. Here we're going to calculate natural log of n plus 1 divided by n plus 1. And after comparison, we can see what kind of n will be appropriate. And we're starting with 10. So we can do natural log of 10 plus 1 divided by n plus 1, 10 plus 1. And we'll see that number, and that's definitely not smaller than 0.01, right? So, okay, so it looks like we do have to increase the quantity. So instead of you solving the inequality, I decided to try with number because the equation itself has this natural number n in there. So we're not solving this for n. We know for sure that n is integer. So you can go 10, 11, 12 until you find n that has this less than 0. Any question? Are we okay? You can also attack this with any number that you think is reasonable. And you can see right now, natural log of 11 over 11 definitely is not less than 0.01. So you can imagine that n should be much, much bigger than this. Right. So I think maybe we should not jump 1 by 1. Maybe we should jump 10 by 10. So we're gonna go whatever is this number with a plus 10. Right? And then we're gonna do the same calculation as in this one, natural log. And it is getting smaller, but not small enough. So I'm just trying to imagine what the number is supposed to be, so it's small enough. A 0.026 is still not small enough. That want to see the tendency with the number is going lower. Should be the n. And this is what happens with the natural log. It's one of those numbers that don't grow large enough. You can see, I think it's maybe I should jump with 100 instead. Okay, let's see, 200. Okay. Still not. So n is really, really large. Okay, that's almost there. That'll be 700, and so you would have to add 700 in a partial sum, and this is definitely not the one I would recommend doing it manually. So it's not very close, so maybe we can go a little bit below. This can also be solved algebraically, not solved algebraically, numerically, but with a computer system. Like what I did with Excel, and then I did make the number grow like every 10 and then every 100. So there's an algebraic system that can give us solution faster. And also do this a bunch of different ways to find. If you are trying to look for a numerical solution, there are several different ways to find a numerical solution. So for example, right now we got a function that goes natural log of n over n, and we can find the solution here. Y equals natural log of, we're doing 8 plus 1, n plus 1 over 1. We can let the computer help us to find the solution. So then the solution would be, we can't do that solution. So long. Solution was 700, so maybe that's small, it's not a good way to present it. Another method will be, it's in there, but I just can't make this look like it's along the line, right? It's
What if we feature?
Yeah. But-
Press that side on top, basically.
Can we zoom out? Like almost like right 90 degree there. Let's see. Right, it was supposed to be crossing 700, crossing the curve in there. But I wanted to see where was that x-intercept? Since the whole line is almost parallel to the x-axis, it's hard to tell what it is. So there's a computer algebraic system called Wolfram Alpha. And that also can do numerical calculation for us. But other than that, I think Excel will be okay. So basically, we're trying to solve this equation that goes logarithm of x plus 1 divided by x plus 1. Want to make it equal to 0.001 to find that solution. And our equation, and that was the solution, which is roughly solution. I'll display. Maybe we can try multiply both sides of the equation by x plus 1. That makes it a little more visible. But anyway, I do believe we don't have to do this as long as we find our solution. 9,000. In the picture, it's really large. Let me see what was being presented. X. $9,118. I wonder, I can't find it, and but our calculation did make it. Oh, that's not smaller than 0.0. We stop at 700. That's That's why. Okay, so this will be the kind of question that probably will not be on our test, but that's the numerical exploration. The ultimate goal is realize this allows us to measure the error, but if you get a equation that's not decreasing as fast, then it's hard to really figure out where that point reached 0.01. The natural log itself is an increasing function, but the n+1 is in the denominator. It's making it decreasing. So between the increasing and decreasing, there's really a curve affecting the curve to the point that the curve is going down, but it's not quick enough. So it looks like everything looks almost horizontal at the curve. So an+1 itself is not decreasing fast enough to the point that if you really want to find the zero, it's not visible in the graph of the function. I don't think that would be a good example, but it did show us that this an+1 is way to model the approximation accuracy. And let's see what we have. Sorry, I probably shouldn't spend so much time on the one that it's not very not simple enough or not very meaningful for this method itself. I say for any approximation question here. I did put some question for approximation. Yeah, so there are a few approximation questions. Let's start with the first one. Might be question 6. All right. If you look at the textbook homework that I assigned, I believe I did assign it because it's open this morning. Okay. All right. So start from question 6. It's looking like this. Right. We are trying to figure out this one is easier because there's only one n in the an+1. So similar to the n cubed 1/n cubed that we had in the example, if we want to find the n that approximate the total summation to be within 0.0001, 10 to the -5 power. So we want a high accuracy in the approximation, which makes sense because the number itself it is already really small, like 1/1, and then 1/2 to the power 6, which is really small already, and then 1/3 to the power 6. The denominator has really high power, which causes an to go decreasing drastically. So even though we want the accuracy to be the 10 to the -5 power, I imagine the n shouldn't be too large. Do you have the same one, or is it 9, the 6 that was higher in power? Do you have the same?
It's similar.
Okay. So anyway, the positive part is the 1/n to the 6th power. So that would be how you model an+1. So let's try to see how the computer, what kind of answer the computer actually wanted us to present, since I do have my doubt for the 9 or 10 in the first example. So we hope to use a partial sum to approximate the total sum. This is how it was in some of the book. The infinite sum is S, the partial sum is S of n. So we're gonna go by that notation right now. So S of n, S of n minus S. Partial sum minus infinite sum is less than an+1. This is only true in alternating series, not in all the other series. If the series is not alternating, then we don't have this. But right now we do have this, and then the an+1 should be smaller than it says at most. This is our error. We're looking for the n, so the error is within, or the error is at most 0.00040 after decimal 1. Okay, but the 10 to the -5 power is the same. So now we can find a way to write an+1. This equation is what we're going to work on for error control. So an is this, the n plus n to the 6th power in the denominator. So an plus 1 will be 1 over n plus 1 to the power 6. So that 1 over n to the 6 is an. That's why an plus 1 is 1 over n plus 1 to the power 6. This is less than 10 to the negative 5 power, which is 1 over 10 to the 5 power. Okay, and are we okay so far? It looks like the inequality is reciprocal on the left and then reciprocal on the right. We can reciprocal of the reciprocal and turn the inequality around. You can also think of it as a cross multiply, and then the equation will still be true. So as a result, after we flip around and turn off the reciprocal, we will have n plus 1 to the power 6, which is bigger than 10 to the power 5. So I'm trying to handle the fraction by using the reciprocal in question. This is one of the inequality relation. Remember, 1 over 3 is less than 1 over 5 is less than 1 over 3. And therefore 5 is bigger than 3. So 1 over 5. Denominator has to be bigger for the reciprocal to be smaller. So that must be a bigger denominator than this denominator, right? The fraction. For fraction, only when these are both positive, only when the denominator is bigger, that's why the whole fraction will be small. Be bigger. And then we want to solve for the n. There's only one variable in the equality. So in order to solve this equality, we'll take the power of 1 over 6 of both sides of the equation. So we can have x n plus 1 is bigger than 10 to the power 5 times 1/6 power. So we're taking 1/6 power of both sides of the equation just to counter effect the power 6. So okay. And then we can minus 1. So n gotta be bigger than 10 to the power 5, 6 minus 1. Now we need to know that number. You might have to pull this into a calculator, but I'm gonna probably use Blackboard as my calculator. And we have to be bigger than this, but right now I'm not sure exactly what number. So using the computer as my calculator and see what it is. So 5.81, it gotta be bigger than this, so n should be 6. Okay, so according to the calculator, then 10 to the power 5, 6 is less than roughly 5.81. Okay, n has to be bigger than 5.81. That's why n gotta be 6. Okay, so now we realize we were supposed to add 6 number in that theory. So now the rest of the calculation, and then you can see how it's being calculated, or you can just start calculating it one by one. The first number in the power in that series, in that alternating theory, is when n equals 1. If n equals 1, the inverse is 1. Negative 1 to the power 2 over 1 to the power 6. The first number is 1, right? The second number must be negative since it's alternating. The denominator will be 2 to the power 6 is over 1 over 2 to the power 6. And then the next one plus, so it's plus 1 over 3 to the power 6. We're supposed to do 6 of these. And then minus, we can do negative power, right? Minus 4 to the power of negative 6. And then plus 5 to the power of negative 6, reciprocal negative 6 power. Then the 6 ones, 1, 2, 3, 4, 5. The term after that is minus 6 to the power of negative 6 power. So calculation. So once you enter it, first enter the fraction, and then I wanted to take the shortcut. I write it was only 1 over 4 to the 6. But I did 4 to the negative 6, but it's easier to enter. But the total summation will be this. It is accurate to the like really accurate. 10 to the negative 5 is really, really small. Any question? I believe the rest are similar to this unless we got problem part. And this is very similar to the one we did on the example. This should be a similar one. I guess this is the last one. We can try one more and then we move forward to the next example. Right, so that's example have a exponential function in there. So to handle the exponential function, we might have to do log result. Okay, so according to this equation, to identify how many number are we supposed to add, we want to make sure that an plus 1 has to be less than this number, less than 0.0001, which essentially is 10 to the negative 4 power. So what's an plus 1? You want to identify the an. So an is equal to 1 over, ignore the sign, e to the power n minus 2. So an plus 1 is 1 over e to the power n plus 1 minus 2. We want this to be less than 10 to the negative 4 power. Question. 10 to the negative 4 power is 1 over 10 to the power 4. Again, smaller fraction have bigger denominator, so the denominator e to the power n plus 1 minus 2 must be bigger than 10 to the power 4. Therefore, e to the n plus 1 will be bigger than 10 to the power 4 plus 2, which will be this 1, 0, 0, 0, 2. And then we want to find the n. You want to take natural log of both side equation. So n plus 1 is bigger than natural log of 1, 0, 0, 0, 2. And of course, n will be bigger than natural log of 1, 0, 0, 0, 2. That's 1. You're going to take the natural number. So, of course, this will be a decimal number, a large decimal number. And that's pretty much the calculation on this one. There's only one n in the equally, so it's less complicated than the natural log over n stuff that we did earlier. Any question? So we okay so far. Second type of problem. I'll leave the rest to you guys, and then if we have looked over here. Yeah, I haven't really moved on to the next topic yet. All right, the title is called Alternating Theory and Absolute Convergence. So next, let's talk about a concept that's called converge absolutely. Okay, so number one, a series summation of an is called converge absolutely if the absolute value of the an added all together converges. So that is, suppose this an is positive. Then it converge absolutely means that the sequence itself, the series itself, converge. Now, if it's alternating, then absolute convergence means that the positive part of the theory converge. Okay. Below it, we have converge conditionally. What is converge conditionally means that the series itself converged, but its absolute value does not. The absolute value of the series actually diverge. Okay, one diverge, one converge, that's what we call it, converge conditionally. If they're both convergent, of course, they'll be converged absolutely. One of the very common example will be the alternating harmonic series. Summation of -1 to the power n over n will be converged conditionally because the harmonic series diverge, but the alternating harmonic series converge. So that will be example of converged condition. Any question? Okay, so here we have a couple of examples. We want to know if they converge or not converge, if they converge conditionally or converge absolutely. Three possibilities: converge absolutely, converge conditionally, or diverge. All right, and let's start with the first one. What do you think? If the first one converge absolutely, converge conditionally, or diverge? What do you think? Converge conditionally, because you see it's, comparable to one over n, right? N over n squared, one over n. So negative one n times one over n converge conditionally, since this one comparable to that one. So this one will converge conditionally. Converge conditionally means that if you don't have the negative one to the power n, it would diverge. Without the negative one to the power n, it will diverge. But adding the negative one to the power n, it's now convergent. So the alternating theory converge, but the absolute value of the series diverge. That's the first one. The second one, second example, what do you think? Converge or diverge? Converge conditionally. Do you mean that without the negative sign, it would diverge? N squared over 2n, is it diverge? Not sure. We can look at the second example since we are. Let's try and see how it is without the negative sign. So now this one, if we're gonna look at without the sign, then you have summation of n squared plus 2n plus 5 over 2 to the power n. N is from 1 to infinity. So that's the absolute value of this, because that is after you remove the sign. All right, so this is comparable to summation of n squared over 2n. N is from 1 to infinity. That's comparable because in numerature, when n goes to infinity, the main component is n squared, right? Comparable. So since they are comparable, if this one converge, this one converge, and therefore that one will be absolute converge, right? Right, these are all tied together. So now let's look at the green one. What we're gonna do, we can do the so-called root test. I see a power n, so we can run the root test. So we take n's root n squared over 2 to the power n. I'm running the root test. Let's do a root test to tell whether it converts or not. And then when n goes to infinity, this is equal to limit of denominator is n root of 2 and denominator is going to be 2. Numerator is going to be n root of n. And then there we can move the square to the outside because operation is associated. Operation can be moved to the outside. So numerator will n goes to infinity, n root of n is power 1, so it's 1 over 2. All right, that means the ratio is actually less than 1. According to root test, what's the result? Limit is less than 1, so this is actually converge. So it's comparable to the geometric test, geometric theory. When the ratio is 1/2, then you have 1/2 to the power n. In the sense that the so this is comparable to summation of 1 over 2n. The n squared is comparably smaller than the 2 to the n power. So this one converge, and therefore this one converge, and therefore this one is absolute converge. That's the second example. Okay. What about the last example? Do you mean remove the sign, it will converge? You said conditionally. You mean the whole thing converge, but having the sign, remove the sign will diverge. That's what you mean, right? See, if you remove the sign, yeah. If we don't have the sign, then 3n over 5n has a limit. And that limit is 3/5, so it's not 0. Right. Therefore, it cannot, it would diverge. But if even with the sign, what will happen? I think, remember the alternating theory convergent alternating theory test saying that if you got an alternating theory, we want this part to be number one positive, number two decreasing, number three converge to zero. That's separate. Yeah, so it's disagree with alternating theory test because it's not approaching zero. So I think this one actually diverge. Yeah. Because the limit is 3/5, it's kind of comparable to -5 to the power n times 3/5. And then it will be alternating, but alternating theory could be divergent if it's approaching two separate values. It's approaching the positive 0/5 and the negative 0/5 as n goes to infinity. So it's not approaching to a single value, and therefore it's not gonna convert at all. So the first one is convert conditionally, the middle one converge absolutely. The last one, the example number 3, would diverge. Another way to tell this is do it numerically. The reason I was displaying this on Excel is because it's really a quick way to see if there's convergence in S to the n. So you can list all the AN and start adding them. If in the S to the n column, the number are approaching a finite number, then you see the convergence, otherwise not. Any question? So this is applying that idea. All right. So absolute convergence theorem saying suppose AN is a theory that converge absolutely. Converge absolutely, it's actually a very high requirement. So it has these two consequences. Number one, of course, the theory itself converge. Number two, suppose you rearrange the term, like the first term move to the third term, the fourth term move to the fifth term, or you can rearrange like let's add every other term you switch them. Okay, and then the result will be, see, it will be the same answer, same summation. Even if you have some negative term, you rearrange them, again, same answer, as long as the theory converge absolutely. So it's result. One of the things we should know that if it's converged conditionally, when you rearrange term, it might still converge conditionally, but the summation might be different. That's the thing, the differences between absolute converge and conditional converge.
Yes.
Rearrange the term and it will create a new sequence. And the theory will also be a new theory, but according to this, as long as you have absolute convergence, the summation will stay the same. That's nice that you realize if rearranging the term is not factor total sum, which should be the case if you have finite number. Like if you're adding a number, the total is 80, and you rearrange them, it's still supposed to be 80, right? But it's not the case in the infinity case. All right. Okay. So basically, this what we mean by absolute convergence theorem. We basically say rearrange the term in absolute convergence theory does not affect the sum. And then that also means the summation of the conditional convergence theory, when you rearrange the term, it will change the value. Okay, sometimes it may even go from any value that you want it to be, even infinity. That's very extreme situation. Right, and here we have an example. If we rearrange the term in alternating harmonic theory, by like adding some of the numbers together, adding these, and that what we happen is here, and then it actually end up equal to 1/2 at logarithm 2. So remember in the original harmonic theory, when you don't rearrange the term, like it was positive, negative, positive, negative, positive, negative. It was natural log of 2. But now after we're rearranging the term, it ended up being 1/2 natural. the alternating harmonic theory is one of the popular examples for conditional convergence. So when the theory is conditionally converged, we can actually rearrange the term in there and can come up with any combination of ways to rearrange term to give you the finite sum to be any number that you want it to be. That's the meaning of it. So it can be really extreme, a big impact. Any questions? So this is how you rearrange it. So it becomes this, and then factor common factor will become 1/2 of the original harmonic theory. We know the original harmonic theory has a summation of natural log 2. That means this actually equals this. But that was a rearrangement of the original theory. So that kind of counterintuitive, because that was the original harmonic theory. If this does not have different value, this will be log 2. That will be like natural log 2 equal to 1/2 natural log 2. We can't have that conflict. So we decided that this cannot be the same value. So we're saying you rearrange the term in a conditional convergence theory, it doesn't equal the same value anymore. That way we avoided a lot of conflicts. Any questions? So that just being a caution, we will not assign any homework on that, but it definitely make a good example, a research paper. If we can come up with new ways to rearrange the terms. Any question? Right, so the first 5 sections are already assigned. We are probably should be ready to finish most of the assignment. I think. Yeah, I should remind you that you guys asked for extra practice on the volume problem that was there. Have you tried any? Yeah. Okay, so it was there. If you want to get more practice on any other content, I can also make extra practice for the question. You should try the multiple choice question just to get a better idea how it is. Then you can avoid the calculation part of it. Just focus on how to set it up. There are a couple of multiple choice questions to practice the cylindrical shell method of this method. So far, the first 5 sections of the chapter 8 is already assigned. Try them. Chapter 8 is normally where one of those chapters the student can regain some of the point that you lost during chapter 7. I was dropping, but I am going to drop the lowest test score. So if you feel like chapter 7 will be the only chapter that you did badly, maybe you should try to do better in chapter 8. As you can see, chapter 8 has some calculation, but calculation is not the only focus. Many of them focus on discussion on divergent converge. So have a common sense of a comparison method, identify the reason why some method works for some theory is a focus. So if it's some thinking and practice, do this. They're not that time consuming. They're not high high calculation condensed. So it's the thinking that's more, and there's a different variety of problems. But try them. The question are not time consuming, but it puts a lot of thinking why this works and why that works. There is a couple of theories and tests. So it's different kind of problems. So I hope that it works out eventually us, right? And that'll be it for today. Thank you. Let's catch up on the homework. I realize we're still have some leftover chapter 7 stuff.
It's going to be sort off on the. Well, I scheduled it. It's not this Monday, but the next, go the 23rd. Yeah, I'll break it down to 150.
Yeah, they have all there. I couldn't tell you what the reflection. What this song. Example was like 11:05, the 5. What is song? do all last night. I did rush. It's quite fine. So, yeah, I'm still kind of really used to. So it's a test. So we get to.
The test allows us to quickly determine whether it's converged or diverged. But fundamentally, what unit theory is to add infinite many numbers, and you want to find out if the summation is a number that we can calculate, finite number. If you cannot calculate a finite number, that will be a divergence. You can actually use Excel to try to figure out if there's any connection between those. So, when you were on 1.8.2, were you able to finish most of it?
I got like, I did all of it basically, but like I didn't get the full grade. I think it was problem 7.
Okay.
Yeah, it was literally some question just like that.
You see that was 9/9 power n, and you can actually bring that 9 outside, and that will be 1/9 to the power n. And then this is a power function, so you can bring the 9 to the outside and summation 1/9 to the power n. So then that will look like, that will kind of change the format, so that if this is finite, the 9 doesn't matter. The whole thing will be fine. So you're gonna focus on this. But remember, summation of R, any number to the power n, make it geometric series.
Yeah.
Right, so we start with 1, so it looks like 1/9, well, this part. A equal 1 is 1/9, and 1/9 squared, and then 1/9 to the power 3, and so on. So it looks like this is the geometric theory. Okay, and then the value conversion to, so this, we have a formula for this. The first term is 1/n. Launchers 1 minus the first, 1 minus the A, 1 minus R. That was the formula, geometric series. We got a formula to handle it once we realize that series. So 8.2 is one of those sections we heavily on geometric series. We have to, so whenever we have a geometric series, we kind of know that we have a plan.
Okay, yeah, I see what I did wrong. It was 11/5, so. Oh, I did, this is. I had 11/5. Got the 9.
Yeah,
And that would help solve for it, would be basically 1/5. Oh, if I'm doing this 1/5.
yeah.
Yeah, I see what's. I'll at the same time always mention that as well. Yeah, but yeah, I think we can get it. Yeah, we have tomorrow, definitely. Is on.